Welcome everyone to today's video. We'll be continuing from our lecture of work energy theorem, and we'll be doing some questions on it. So in work energy theorem we learned that work done by all forces is equal to change in kinetic energy of the body. So let us try to apply those concepts in some questions. So the first question which we have is that of a particle. So we have a particle whose mass is given as some 0.5 kg, and we are given the expression for the velocity of the particle in terms of its position. So let us write that expression. So the mass of the particle is some 0.5 kg, and the velocity of the particle is some ax की power 3 by 2, where the value of a is given as some 5 and its appropriate units m minus 2 and s की power minus 1. So this is the expression for velocity of the particle, that is ax की power 3 by 2. Mass of the particle is this, and we are to calculate the work done by all the forces acting on the particle between the points x is equal to 0 and x is equal to 2 meters. So definitely there should be some forces acting on the particle. Why should there be forces acting on the particle? So the force should be acting on the particle because its velocity is changing. Velocity is changing, that means there is some acceleration. There is some acceleration, there has to be some force. So we have to calculate the work done by all forces on the particle. Now as such there is no hint to us what forces are acting or what is the magnitude of force. So this is the idea of work energy theorem, that without going into detail of the forces we can calculate the work done of them. So how this is possible? So we use the work energy theorem, which says that work done by all forces is equal to change in kinetic energy. So we know the mass of the particle, we know the velocity of the particle, that means we can write the kinetic energy of the particle. Initially, so final kinetic energy of the particle is some half mvf square minus some initial kinetic energy of the particle minus half mvi square. So work done by all forces, that will be some half mass of the particle is some 0.5 into final velocity squared, so that would be some a squared, and x की power 3 by 2 squared, so that would be some xf cube minus xi cube. So this comes out to be some 1 by 4, a is 5, so that is 25 into x, the value of final position of the x is 8 2. So when 2 is cube, it comes out to 8 minus 0. So this is 25 times 2, that is 50 joules. So we have substituted the value of velocity directly in the expressions, and we have directly used the work energy theorem to get our answer, that how the work done by all forces can be calculated. So this is our first question. Let us do our next. So the next question, we have a raindrop. So we have a raindrop of mass 1 gram, and it is falling from sky from a height of 1 kilometer. From 1 kilometer height, a raindrop is falling. So after falling through a distance of roughly 1000 meters, it strikes the ground with a speed of some 50.0 meters per second. Action due to gravity is given as probably 10 meter per second square, and it is given that the raindrop started with 0 speed. So what are the forces acting on the raindrop? Gravity. And what other force? So that other force is the viscous force. When a fluid or a solid travels through viscous fluid, then some resistive forces act on that body. and that resistive force is proportional to the speed of the body. So that particular force is again not given to us, just like the last question. So we have to evaluate some kind of work done acting on the body, and we have to do that without going into detail of the forces. So that is the whole point of work energy theorem. So definitely we can talk about the work done by gravity, because we know gravitational force is simply mg. The mass of the drop is some 10 to the power minus 3 kg, it is 1 gram. So first part is calculate the work done by gravity in going from this point to this point. So that should be pretty easy. What should be the work done by gravity? Work done by gravity can be represented like this, W and the subscript G, that is work done by gravity. So what is the work done by gravity in completing this whole motion when the particle is travels through a distance of 1 kilometer, starting from starting point to the infial point? So that would be the gravitational force, that is mg, times the displacement of the particle, which is h. So this would come out to be some 10 to the power minus 3, that is the mass. Actually gravity is 10, h value of h is 10 to the power 3 meters. So you have to convert this in meters. So this comes out to be 10 joule. The next part of the question is what is important to apply work energy theorem. The next part of the question says that you have to find the work done by resistive force. Now normally if we are only studied up till the chapter of laws of motion, this wouldn't be possible for us, because we would be searching for the force, what the force is, how would we calculate multiplying force with displacement, then we will be calculating work done. But beyond the idea that force is proportional to velocity, nothing is given to us in this question. So we can take constant proportionality and that solve it, but that constant would again remain unknown. So how would we do in that case? So that is where work energy theorem comes into play. We are given that the particle is reaching the bottom with the speed of 50 meters per second. So there should be some use for it, and that itself gives us a hint that work energy theorem is going to be used. So work energy theorem says that work done by all forces is equal to change in kinetic energy. We know the final kinetic energy and initial kinetic energy. The work done by all forces is how it is written. That is what we have also to run. Work done by all forces include all the forces acting on the body. So that means work done by gravity plus work done by the resistive force acting on the body. So we have to write both the expressions of work of the force contributed by the work, that is gravity and resistive force, and we have to add them and we have to equate them equal to the change in kinetic energy of the drop. So work done gravity we already know, that is 10 joule. Work done by resistive force is the unknown. The final kinetic energy of the drop is mass of the drop 10 to the power minus 3 and velocity squared, which is 50 squared. So this comes out to be some 10 joule plus work done by resistive force equal to some 1.25 joule. So this comes out to be some minus 8.75 joules. So the negative sign indicates that the work done by resistive force is negative. That is, the viscous force acting on the drop is in upward direction and the drop is traveling in downward direction. So that is what we have obtained correctly, and its value is less than the net work done by the gravitational forces. That is also what we are expecting. The particle started with zero kinetic energy. So that's why delta K is simply half mv square only. We do not need to write initial kinetic energy. And the work done by resistive force is slightly less than that done by the gravitational force, because gravitational force is trying to increase kinetic energy and resistive force is trying to decrease it, take it away. So definitely work done by resistive force would be some value, but since we are having some kinetic energy up till the final point, it would be slightly less than the work done by gravitational force, because it would try to leave some kinetic energy in the drop. So that's why it's moving at some speed 50 meter per second. If it were the case that the drop is reaching with the ground with no speed at all, then we can directly comment that the resistive force has completely negated the work done by gravity and they are completely equal. So that would also be we can see from this expression only. So that is how work energy theorem works. So let us move on to the next question. So next question, we have a ballistic demonstration. So in a ballistic demonstration, we fire a bullet at a plank, and that plank slows down the bullet. So that is our objective. We have to find what is the final speed of the bullet. So this is a plank in which some bullet is fired with some speed, and the resistive force provided by this plank is given to us. The resistive force provided by this plank is some 45 kilonewtons, a pretty high force, and the thickness of this plank is, that is the displacement, is some 2 centimeters only, very thin plank. So it is given that the speed with which the bullet is fired is 200 meter per second. Obviously the bullet would be some fast bullet, otherwise what is the purpose of it? And the mass of the bullet is some 50 grams. So the bullet is of 50 grams, its speed is this, resistive force provided is this, and displacement is this. We have to find the final speed of the bullet after it has perforated this plank. So we will be applying work energy theorem, work done by all forces equal to change in kinetic energy. So the only force working here is the resistive force, and is working in direction opposite to the displacement of the body. So it is a negative work. So the force acting on the body is 45 kilonewton. That is 45 to 10 to the power 3 into the displacement of the body, that is 2 centimeter, 2 10 to the power minus 2. So this work done should be equal to the final kinetic energy of the bullet, let's say Kf, minus the initial kinetic energy, that is half mv square, half mass of the bullet, some 50 gram, 10 to the power minus 3, into the displacement into the velocity is 200. So that will be some 4 10 to the power 3 meter square. So solving this, we will get some minus 900 joule is equal to final kinetic energy minus some 1000 joule. So that means the final kinetic energy of the bullet is equal to 100 joules. So we can say that the bullet has lost 90% of its initial kinetic energy. Initial kinetic energy is lost. Right, this is what we can say. The initial kinetic energy was 1000 joules, and 900 joule of energy is lost. The remaining energy is 100 joule. So this loss of kinetic energy is usually converted into the heat of the block. That it gets heated up and it is producing a lot of, and some sound comes out from the plank and so on. So again we calculate the final kinetic energy of the bullet by simply using the principle of work energy theorem. We will be finishing the questions with one last question. So the expression which we took to solve this all the questions was work done by all is equal to delta K. The last question is that of a block. So we have a block, it is having some mass and it is traveling on a rough surface. Again it is experiencing some resistive force. A block is kept on a surface, and let's say there is some origin x equal to 0. From x equal to some 0.1 meters, I guess, it starts experiencing a rough patch, and up till the point x equal to 2.01, it continues experiencing a rough patch, and after which it leaves the surface. So we are giving the mass of the block the mass of the block is some 1 kg, and yes, mass of the block is 1 kg. It enters a rough patch with the speed of some 2 meters per second, and the resistive force in this case, we have been seeing that this resistive force is a common feature in the questions of work energy theorem. So that is what is usually the use for work energy theorem. In a lot of questions that you have some resistive force which is not known to you, calculate the work done. So usually our mind travels in that direction. Okay, there is some force F dot dx, that is work. So we have to look for the force, but the force is not there. So how would you find the work done? So in that case, always remember your option B is work energy theorem. Option 1 is always to multiply the force with displacement and trying to find the work done in that way. And that is the first idea. But when force is not given, try to use this approach. And most probably this approach would yield you the result which you want. So the resistive force acting on the particle is some minus k by x, where x is the position of the particle away from origin. So again, repeating the rough patch, where the rough patch is from. The rough patch is between 2.01 meters and 0.1 meters, and the value of resistive force is 0 otherwise. That is what is written. Otherwise it is 0. Between these two values, it has the value minus k by x. The velocity is given as 2 meters per second, and the Fr is the retarding force in this case. The value of k is given as 0.5 joules. And we have to now solve to find that if the block started with a velocity of 2 meters per second, what is the final speed of the block? That is what we have to do in this question. So applying work energy theorem, but here we are given the force. So we will say work done by all forces is equal to final kinetic energy, that is half mv square vf square minus initial kinetic energy half mvi square, and value of mass is 1 only. So we will be integrating Fr dx from 0.1 to 2.01. So again, one more expression it is given to us, natural logarithm some 20.1 is 3. So this is equal to half vf square minus initial velocity of the particle is 2. So vi square, that is 2 square divided by 2, that is 2 only. Fr is the negative value. So minus kx integral 0.1 to 2.01 is equal to vf square by 2 minus 2. So integration of 1 by x, k would come outside. The integration of minus 1 by x is ln x, and it would come out to be ln 2.01 upon 0.1. So I hope that is clear to you guys, that 1 by x is integration of 1 by x dx is simply ln x. So that would come as ln x, k is outside, and and putting the limits of value, putting the limits in ln x, that is 2.01 divided by 0.1, that would be 2.01 divided by 0.1 would come out to be ln 20.1 only, which is exactly equal to 3. So this would come out to be minus k into this value, which is 3, and this is equal to final velocity vf square divided by 2 minus 2. So in the next class we will be starting with the idea of spring force, that how springs work and what is the spring force. So minus 2 went here, it became half, and the value of final velocity of the block after it has crossed this particular distance is 1 meter per second. So this is how we approach the questions for work energy theorem, and a lot of variety of question comes on work energy theorem. For example, some spring is involved, so that we'll be able to do after the next lecture only. But the idea will be know that all the forces are to be combined and we equate with the value of delta k. But through your own effort you can also solve questions of work energy theorem, because there are a lot wide variety of question available on it, and they give you insight in what is the actual use of this theorem, and in what case which we use, and what the case we prefer to use FDX. So thank you for watching and have a great day.